All right, this video is for the lesson 2.10 homework. We're testing how accurate a linear model is using different representations. So today we're going to test how accurate our linear equation is, like using a scatter plot. Okay, so number one, what's the name of the ratio of the difference in function values compared to the difference in input values between two data points? So that's average rate of change. That's what we did. That's what we did the other day. And then what is the name of a measure of the steepness of a line on a graph? That's the slope. All right, so we're going to use this table to answer the bottom questions. Okay, it says, what is the average rate of change for the table? This is what we did the other day. Okay. And so it's tedious on this because these tables are big. And so this is where we have to subtract backwards on all of these. And so again, it's more tedious than anything else. Okay, so 1.621 minus 1.639 is negative 0.018. 1.595 minus 1.621 is negative 0.026. Next one is 1.583 minus 1.595 is negative 0.012. And then 1.543. And again, it's just subtracting backwards is all I'm doing on this table. Negative 0.04. I should have done this ahead of time and just had these values for you. Didn't plan very well. All right, kind of getting where you can't see. 1.486 minus 1.515, negative 0.029. Move this calculator over. And then the last two, 1.474 minus 1.486, negative 0.012. 0.435 minus 1.474 is negative 0.039. So we've got all of these values. We're going to add them up and divide by what we have. So I'm trying to get them. Yeah, those all fit there. All right, so we're going to add them up. Negatives everything. Oh, is that a 2.6 or a 1.6? Hoping it's a 2.6. And I didn't get the negative in there. Zero 0.029. Okay, so we get negative 0.18. We've got 1, 2, 3, 4, 5, 6, 7, 8 numbers, so we divide by 8. And that's our average rate of change. Again, it's just tedious. So negative 0.0255. So if I wanted to write an equation, I would do y equals, and I would take that average rate of change, slap an x behind it, and then I can pull the y-intercept from this table, plus 1.639. Okay, so I can create a scatter plot. I'm actually not going to draw it on here. I'm going to use Desmos to show you. Desmos is a really cool graphing calculator that actually graphs in a lot better format than what even those calculators do. And so you can put ordered pairs into Desmos where you can't do that on our graphing calculators. And so these are just the values from the table. This table right here. So that was that first value. So this one, 1 comma, and that's all I would do is just parentheses, 1 comma, 1.621. And I can graph all of these points. Again, should have done this ahead of time so I could have just shown you. Oh my goodness. Today's one of those days where I shouldn't be allowed to teach math. My brain shuts down after a certain point and I go number dumb. And then I get frustrated and then I get mad. It'll depend if we've got somebody else that can take it over.
I'm hoping nobody's taking it over, but
who else would take over? Hey, just put us in a study hall.
You have to have a full year of math your senior year.
Hey, that was our year right there.
No, sorry.
We didn't do anything.
It's a time thing.
yeah, give us back to Scoggins.
Please.
That'd be great.
Let me at least get you through the TSI first. Because that's more important than anything else, right? Okay, so here's all those points. And then I can also type this line in. And what I can do, I can kind of zoom in on this and see how well those points line up. And so you can adjust this thing. So I just want it to go from, let's see, the x-axis, I want it to go from -1 to 9. And then the y-axis, I just want it to go from -1 to 2. But anyways, you can kind of see that some of these dots, and it's still kind of hard to see on there. Some of these dots are sitting like above the line. So you can kind of see all of them aren't sitting nice and pretty and perfect on that line, but they're pretty close. They line up pretty well. And so what that means is using this scatter plot, I can tell that, hey, this guesstimate that I made using the averages, it's pretty close to the data. It represents the data really well. And so we can use the X values from the table to determine if the linear model is accurate. So we can create a table for this equation too. And that you can do on your regular calculator. So you can just type the line in. We can graph the line that we created here. So -0.0255x plus 1.639. And we can pull up the table. And we just copy these values down. 1.6135. Yep. And then 2 is 1.588. 3 is 1.5625. 4 is 1.537. 5 is 1.5115. 6 is 1.486. 7 is 1.4605. And then 8 is 1.435. So the last question says determine the accuracy of your function. And so again, looking at that graph we made, everything lined up pretty well. And then we can also just kind of compare the values. And as long as they're pretty close, we're still about 1.5. This one's a little bit off, but not too much, 1.4. Then we've got a pretty accurate model. So I would say that this one is accurate. But again, it's just using one of these, like the average rate of change, to get an estimate. And then graphing that line against the actual data just to see if things line up, if it looks right, if it matches. Under 6 is 1.486. Sorry, yeah, that's...
What about
7 is 1.4605. 1.435. Does that help? Okay. All right, so the back side. We're doing the same thing again. So this one, I'll tell you, I don't think this one is accurate. I think this one is... Oh, this one is accurate too. Not as accurate. You'll see what I mean after we graph it. Okay. So I'm not going to go through the whole process because I already did it on the other one and it's tedious. Okay. But going through and subtracting backwards and then dividing by what I have, the average rate of this one, the average rate of change is 0.145,625. So the function rule, we would use that average rate of change, slap an X behind it, and then the 0 value, that's my y-intercept. Okay. I wish I had one that was not accurate so you kind of see what those look like. And so I'm just going to graph again like I did on Desmos. I'm just going to start over here. And I'm going to graph the points from this table here. So I've got 0, 2.090, and then I've got 1, 2.168, 2, 2.326, 3, 2.496, 4, 2.791, 5, 2.839. Let's see. Ooh, that one's off. 2. Okay. I really messed up on that one. There we go. 6, 2.972, 7, and then 8. Okay, so there's my points, and you can see they're not as straight as those other ones were. And then I can graph this equation that we estimated. And so again, looking at it, comparing it, it's still pretty close. I mean, this point is kind of wonky, it's way off. But when we say accurate or fairly close, the dots are following pretty much the same path. If it wasn't accurate, it would be something like that. You know, none of the dots line up nice and neat. That would be not accurate. But if the majority of the dots pretty much hit that line, we've got an accurate model. Hey, this represents the data pretty well. And so, and again, we can compare the data with the table. You can graph it in the graphing calculator. Control-T pulls up the table. I'm going to try to use a thinner pen here. Actually, I'm not even going to do the table on this one. Doesn't matter. But this one is fairly accurate. And you can use different levels like that. Like the last one, that thing was pretty darn similar, pretty accurate. This one, they were a little wonky, so you could say fairly accurate. You could say, no way, not remotely close. But this is what we're doing for the next 3 days. It's just kind of testing this average rate of change using different methods to see how close it is to what it should be. Okay? All right, so make sure your name's on that sticky